Hey everyone, this is Dr. Walker. This is video 559, RC circuits discharging a capacitor. Let's take a look at the concept. First, let me remind you what we did in the previous video. When we were charging a capacitor, we had a battery, a capacitor, and a resistor. So now we are discharging the capacitor. There's no battery. So that's the first thing to remember. It's the easiest way to tell if our capacitor is going to be charging if there is a battery or discharging if there's no battery. Okay, so what happens is the capacitor is initially charged. When the switch is open, the capacitor just holds on to all of its charge. There's nowhere for it to go. Let's look at what happens when we close that switch. That's this bottom picture here. So initially, there's going to be the full potential difference across the capacitor. So that means that when the switch is closed, that resistor is getting that full potential difference. So the current in the circuit is given by Ohm's law, V0 over R. Initially, the capacitor has its full charge, which we call Q max. Now, what happens after the switch is closed? Well, the capacitor is going to start to discharge. So the charge that was on here is going to flow through here, and there's going to be some collisions in the resistor, and there's going to be some energy dissipated as heat. So it's going to discharge through the resistor. What about after a long time, after the switch is closed, and there's no more charge left on the capacitor? So this means that the capacitor is fully discharged. If there's no more charge left on here, then there's no current in the circuit, there's no charge on the capacitor. And what's the potential difference across the resistor? Well, potential difference equals IR, so if there's no current in the circuit, then there's no potential difference either across the resistor or across the capacitor. So that's the concept for discharging the capacitor. Now let's take a look at the equations. Since we already did this for charging capacitor, we might skip a few details here because it's very similar to charging the capacitor. When we did charging the capacitor, we used Kirchhoff's loop rule to come up with this equation. So now that we're doing a discharging capacitor with the only difference being that there is no battery, we can just say, okay, we're going to start with Kirchhoff's loop rule for discharging capacitor, and this is our equation. And now we need to go ahead and isolate charge, and just like before, we know that the current here is dq over dt. So let's go ahead and do a little bit of math here. Minus q over c equals IR, but I is dq dt. Let's go ahead and divide by R, divide by Q, and get dt to the other side. So we're going to have dt, we're dividing by R here, so R over RC, and we can keep the negative here. And then we're going to divide both sides by Q as well, so we're going to get dq over Q. And now we are ready to integrate to get the Q by itself here. And this is where we have to be careful with our limits of integration. We can't just say 0t, 0 to t, and 0 to q, because we have to think about what is the charge at time is 0, what is the charge at time is equal to t. So at time is equal to 0, the charge is not 0 since we're fully charged at time is equal to 0. Time is 0 is the instant we close that switch. So we actually have Q max to begin with, and then at time t, that's where the charge on the capacitor goes down to Q, whatever that number is. So now when we perform the integral here, we're going to get negative t over RC on the left, and then on the right, we're going to get log of Q max, log of Q minus log of Q max, which is log of Q over Q max. And now we can go ahead and take the exponent to get rid of that log. We're going to have e to negative t over RC is equal to Q over Q max. and we can solve for Q. This is Q as a function of time. We're going to multiply by Q max on both sides. It's going to equal to Q max times e to the negative t over RC. So I didn't have a good picture for it, but what this is going to look like is just like what we saw for current in the charging a capacitor. We start off with maximum charge, and it's going to decay down to zero charge after a certain amount of time. Now let's take a look at the current in the discharging capacitor. So we just found the charge as a function of time, and now we have to use the equation that the current as a function of time is the derivative of Q with respect to t. So let's go ahead and differentiate. We're going to differentiate here the exponent, so we're going to take the derivative here. We're going to get negative 1 over RC times this exponent, and let's not forget our Q max here. So Q max e to the negative t over RC, that's our derivative. Now Q max over C, if you think about it, that is the maximum voltage across the capacitor, right? When the capacitor has its maximum charge, then we have delta V equals Q over C. So that is the max voltage, which is V naught. And then V naught divided by R is just I naught. That's just the maximum current. So we can also write this as negative I naught times e to the negative t over RC. And the negative just means that the current is flowing in the opposite direction that it was flowing before for the charging circuits. But my preference is just to look at the magnitude of this and really not worry about the negative. I never used a negative, because the graph for this is that the current is decaying as a function of time the same exact way that it was decaying when we were charging the capacitor. It's just going to be in the opposite direction, but the graph is going to look the same. So I just like to look at the magnitude of the current. And finally, let's look at the voltage. When we have our discharging capacitor, we can use the same process that we did before. We can use the equations that we just found for current and for charge as a function of time to get the voltage across the resistor. This is using the current equation and dividing it, the current equation and multiplying it by R, right, to get V. And this one is using the charge equation, and I can't do this in my head here. Let's see, C equals Q per V. So delta V is Q per C. I always have to write it down. So using our charge equation that we just found and dividing it by C to get this equation. So the voltage across the resistor looks like this, and the voltage across the capacitor looks like the same thing. That makes sense because whenever we have the full voltage across the capacitor, the resistor is getting the same exact voltage, and as it decays, as we discharge, then the resistor doesn't get as much voltage either.